Okay, so let's take a look at bonding types. So atoms have energy levels in which electrons move around the nucleus. So let's take a look at the maximum number of electrons per energy level. So this is trying to show these energy levels, and this is where that planetary model really helps out in this. All right, so the first energy level, which you see here and here and here, can only hold 2 electrons. So, so hydrogen only has 1 electron, so only 1 goes in there. Here is carbon, which has 6 electrons, and so 2 are in its first energy level, 4 in its second. All right, so here's oxygen, 2 in its first, and then 6 in its second. So the first energy level can only hold 2 electrons. The second energy level and up can hold 8. Now, if you take a chemistry class, you can learn about these sublevels and stuff like that. We're not worried about any of that. All right? So what we're going to say is an atom is most stable or unreactive if it has a full outer energy level. All right? So once these atoms, they want a full outer energy level. And so what atoms will do is they're going to gain, lose, or share electrons to get that full outer energy level. All right, and this is what's going to create the bonding. So the first type of bonding is what is known as ionic bonding. All right, and this is a chemical bond formed by the transfer of electrons from one atom to another. Okay, so let's take a look at this. Here's sodium. Sodium has an atomic number of 11, so it has 11 protons, 11 electrons. All right, so it has 2 electrons in its first energy level, 8 in its second, so that's 10. So it has 1 more electron in its third energy level. Chlorine down here has atomic number 17. So it has 17 protons, 17 electrons. So with its electrons, it has 2 electrons in its first energy level, 8 in its second, so that's 10, and then 7 in its third, so that's 17. All right? Now sodium up here, it could gain 7 electrons or lose the 1. And it's much easier to lose 1 electron than to gain 7 to have a full energy level. In chlorine over here, it has 7 in its outermost energy level. It wants 8, once again. So it could lose 7 or it could gain 1. It's much easier for it to gain 1 than lose 7. So sodium gladly gets rid of that 1 electron. Chlorine gladly takes that 1 electron. So now sodium has a full outer energy level. It's happy. Chlorine has a full outer energy level. It's also happy. All right? So what this does then, by that 1 electron being transferred from one atom to another, now sodium has 11 protons, only 10 electrons. So 11 protons, 10 electrons, more protons than electrons, positively charged. Chlorine here has more electrons now than it has protons, 18 electrons, 17 protons, so it becomes negatively charged. All right? And so because now this is positive and this is negative, these opposite charged atoms are attracted to each other. All right? So that's what forms the bond. All right? And so these are ionic compounds. What we see with ionic compounds is one of these atoms is positive, the other is negative on those. All right? So that's what we looked at with atoms here, and they could gain, lose, or share electrons to have that full outer energy level. Here, 1 gained, 1 lost. So now let's take a look at sharing. So in sharing, this is called covalent bonding. So this is a chemical bond formed by electrons being shared by atoms. Now this isn't one of my favorite pictures of this, but this is showing 2 hydrogen atoms. Each hydrogen atom has 1 proton and 1 electron. And so when they come together, both of these hydrogen atoms are going to share those 2 electrons. All right, so they both have a full outer energy level. So they're happy. Okay, a type of covalent bonding is what is known as polar covalent bonding. And this is a chemical bond in which electrons are shared unequally. And this is what we see with water. So what happens here is these electrons that are shared between the oxygen and the hydrogen, those electrons are actually a little closer to the oxygen atom than they are to the hydrogen atom. All right? And so what that does is it makes the hydrogen atoms slightly positive, which is trying to show there, and the oxygen atoms slightly negative, so I'm showing it there. All right? And so this is polar covalent bonding. So in covalent bonding, what we create are molecules that are non-polar. All right? They don't have a charge throughout. In polar covalent bonding, we create polar molecules. So they have a positive end and a negative end to them. All right? And this is going to be important when we talk about what like dissolves like. So polar molecules, like water, can dissolve other polar molecules, like sugars, but they can also dissolve a lot of ionic molecules, like salts. All right? What they can't dissolve is they can't dissolve oils, which are nonpolar molecules, because nonpolar molecules do not have a charge. All right, so this polar covalent bonding leads to another type of bonding, which is known as hydrogen bonding. And this is between molecules. All right, so here you have a slightly positive hydrogen atom on one molecule is attracted to a slightly negative atom on another molecule. All right, and this is what we see once again with water. So here's that slightly positive hydrogen atom on one molecule being attracted to a slightly negative atom on another molecule. Okay, so this can occur also within a larger molecule, and this gives proteins three-dimensional shapes. If you heard of DNA being a double-stranded helix, those two strands are held together by hydrogen bonds. Okay. All right, so let's take a look at acids and bases. So an acid is a substance that releases hydrogen ions in a solution. Okay, so if we look here, so this is an acidic solution, a lot of hydrogen ions here. So if you take hydrochloric acid, you put it into a solution here, it will separate into hydrogen ions and chlorine ions. Next is a base. A base is a substance that releases hydroxide ions. So hydroxide ions is a hydroxide ion is an oxygen and hydrogen together, and together they have an overall negative charge to them. Okay, so a pH scale, which is on this previous picture here, right here, a pH scale is a scale that measures the hydrogen ion concentration of a solution. And the scale goes from 0 here up to 14, all right, where 7 is neutral. All right, so right in the middle, 7 is neutral. Above 7 is a base, below 7 is an acid. All right, so pure water is neutral, and pure water is neither an acid nor a base. So if we go back to this picture, this is showing a neutral solution. All right, so with this, what water will do is it will separate into hydrogen ions and hydroxide ions. But these can cancel each other out and become back into water. All right? So that's why pure water is neutral. Okay? And in this, we see the number of hydroxide ions and the number of hydrogen ions are the same. So we say something is acidic, we're saying it has more hydrogen ions than hydroxide ions. If we say something is basic, it has more hydroxide ions than hydrogen ions. In fact, this goes by orders of magnitude, all right? So where 4 is 10 times more acidic than 5, 5 is 10 times more acidic than 6, so 4 is 100 times more acidic than 6, and so on, all right? Now if you look at, a lot of this stuff here, you can see urine is typically acidic, black coffee, tomatoes, vinegar, cola, beer. Now, why we see cola, beer, even wine would be in here, is that all these things have carbon dioxide in them. If you take carbon dioxide and you mix it with water, it produces an acid called carbonic acid, all right? And so this is why all of these carbonated beverages are acidic, because they have carbon dioxide in them, all right? Now, this is very important for us because we exhale carbon dioxide. So one of the ways we regulate our body's pH is just through our breathing. We exhale out more carbon dioxide, our blood is going to become more basic. If we slow down our respiratory rate, we're going to keep more carbon dioxide in us, and we're going to become more acidic. And our blood pH is 7.4, all right? And so we maintain that, and this is very, very important that we maintain our arterial blood pH at 7.4. Because if we get it to 8, well, we're dead. If we get it to 6.8, well, we're dead as well. So our breathing rate and urinating out excess hydrogen ions is a main way in which we regulate our body's pH. So that's very, very important. Okay.